Hello everybody, not good morning. It is dependent of when you look this video, if it's good morning or good evening. If you are live now, then hello and good afternoon. How are you? Say hello in the chat so that I know that you can hear me properly. We are still in this topic here where we work with JSON data in the relational database. Yeah, there are now the chat messages incoming. Could still be good morning. Yeah. Students. Why do students go in the supermarket at 7 o'clock? No. How does this joke go? Why why do students wake up at 6 o'clock? Because at 7 o'clock the supermarket closes or something like this. Don't know. Okay. Let's talk about JSON instead. We are in the chapter about the JSON data type within relational database management systems. And in PostgreSQL, we saw that we can say this column is of type JSON. Then it's basically an alias for a varchar or text column, but it checks for well-formedness, that we can only store well-formed JSON documents in there. And we have functions that we can use on the JSON data type. But PostgreSQL also supports a JSON-B data type, which stores JSON as a binary format, and we have more functions and it's more performant. Here are some operators to access some fields, for example, from a JSON object, or to access an element in an array, first element with a 0 and so on. We had this operator here, which checks whether the JSON document on the right of this operator is part, basically a sub-document of that that's actually stored in the column profile in this case. So it checks whether this document contains this document. So it's okay that we have additional fields here, additional elements in that array. This would evaluate to true if profile is a JSON document that has at least the field hobbies, and within that field hobbies it should have the array element yoga. So it should be of data type array, and in that array should be the string yoga. This is very universal, and we will see that indexes support this operator as well. Then we looked at path expressions. Path expressions are nice when you have predicates and you want to execute those predicates, evaluate those predicates as early as possible. So this is one single operation to check whether a JSON fulfills a given predicate. Other possibilities to do that would be doing this in SQL, so extracting the values that are in this hobbies array and then afterwards checking if it is yoga. This is unnecessary because so many hobbies are not yoga, so accessing them is not necessary, and basically in the end you have multiple operators. Here it's just one operator, so this makes it kind of easier. So we had this question last time. Path query expression is this one here. We go to the first element and access it not as a text, but as a JSON path query returns JSON. So it should be this here. Yeah. No. Yeah. Yeah. We had this discussion last time. This would return the first hobby as a text, and this would return the first hobby as a JSON. So I have to change this. This is more true. Yes. We saw how to unnest the data, and today we will talk about indexes. So an index is a data structure that can help us to answer queries faster. And an index in a relational database system is so nice because the database management system decides when to use it and when not to use it. So we create the index, and then after that we simply write our queries like before. So we write our queries independent of if there is an index or if there is no index. So the idea is somebody writes an application, and then this application works, but it is kind of slow. And then a smart person says, we can accelerate it because there is a where predicate, where city equals London. Let's make an index on the city column. Then b plus tree is created with all city values. We find in logarithmic time all people who live in London, and then pointers show to point to that rows that fulfill the predicate. And the application looks like before, as if there would not be an index. It is just faster. Now with indexes on JSON data, it's quite similar. So the idea is we create an index and then we accelerate operations on JSON data, but not all operations are supported, and only if the index looks like this, and only if the query looks like that, and so on. So here we have to work closer together when creating the index and using the index. So using the index is now a bit more an active task. You have to know how to make use of the index. In NoSQL databases, where we will talk about later today, there are also, in some NoSQL databases, there are also indexes. And when you work with relational databases, it's so nice. You create an index and then your queries are faster, period. In RIAC, a key value store, when you create an index there, you have to say in a query that you want to use the index now. Isn't that ugly? You need to manually say that you want to use this index. Yeah, here it is just used when the database system thinks it is useful to use it. In my opinion, PostgreSQL is the most advanced database system regarding to indexes on JSON data. I say in my opinion because maybe there are some fancy stuff that I don't know for other database management systems or some extensions, but I like it how it is in PostgreSQL. First of all, they introduced a new index type. Maybe you know already index types. So the basic syntax of working with an index is create index. You can give the index a name. Let's say my index. This is not required in all database management systems to give it a name, but names are good for dropping. I always say names are good for dropping. Drop index, my index, and then it is gone. So you give it a name just for that it has a name. It is not so important. if you look in an execution plan, you see this name, this index, my index was used, or if you see an error message or a log message and you see there's your index name, therefore names are good. But it has not so a big role here. Create index, then you say on the name, let's say the table is called people, and then you specify the column, for example, city. This creates an index on the city column. Using specifies which kind of index should be used. When you don't specify a using clause here, a using option, then using B-tree is the default. So B-tree will create such a tree. We look for all cities, and then it builds just such a tree. And such a tree allows equality search. So you ask in a query where city equals London, and then, okay, this is my index on the city column. Here is an M, and here is an D, and here is an O. So L, like London, is between D and M. So I follow this path, and then I find the rows here. So you find all matching rows here, and then you follow these pointers to the rows that have city London. So in your table, you quickly find what you're searching for. This is how an index works. It also supports where city greater than equal L and city smaller than LM. So basically a prefix search. Find all people that live in a city. So this is basically like a like predicate where the city starts with an L. So this is also possible. You go to the first one that starts with an L, okay, this one here, and then you follow on the leaf nodes to that pointers until you find the first one with an M, and then you follow again all pointers here to find all people starting with an L. So this B-tree does not only support equality, but also greater than, equal, greater than, smaller than, unequal, between. Some database management systems also the like with a prefix search and so on. Yeah, the cost is logarithmic, so logarithm to the base of k of n. You have n tuples in your table, so this is how many tuples you have in your table, n tuples, and then it costs logarithm to the basis k, and k is basically the number of pointers you have in each node here. So when you have k is 500 and n is 1 billion or so, the cost is just 3 or 4 or something. So it is a very low cost. But you can even decrease the cost by saying I want a hash index. Hash is not in O of log k of n. An hash index is in O of 1. So independent of how large your table is, the cost of accessing a specific row is always the same. That's very nice on the hash index, also supported for PostgreSQL and Oracle and so on. But this is not the default, because you must be clear. It only supports equality. It only supports where city equals London. City greater than, smaller than, price less than, something between, and so on is not supported. Hash only supports equality, because a hash function calculates hash of London is something blah 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 37. So we jump to something in memory on address 37 to find the information where the row is. That's the idea. And now in Json, two, I think, Russian people, or at least one Russian person, introduces the GIN index, generalized inverted index, and this generalized inverted index can be used on JSON data. Inverted indexes are not new. Inverted indexes are there for a very long time. Let's take a text. Where do I have an example text? Here's something. And because inverted index are mostly used for text data. Yeah, this is good. Here. This is very small. Oh, it's not possible to make it like this. Okay, I hope you can see it. So let's say you store in a column this text here. You have a column of type varchar or whatever. And you can then say, let's say the column is called text. You can then afterwards say where text like free. Okay, you're searching for the term free. These are rows in the table, and this row here would match because here's the keyword free. Okay. Inverted indexes work like this. Word for word, it says it inserts the word and inserts it in a tree. So we in the end have a tree like before. So, and if these are 100 words here, no, these are 30 words, 30 entries in that index reference this one here. So it is called an inverted index because here we have our original data. It says the device may only be operated in try and so on. This is the opposite of inverted, and now we invert it. Now we have the opposite here. Then we have all words in that leaf level of a tree. So it starts with for example the word and then it points to this document because this document contains the word and then here's another and here's the word a, so this points to that document. So this is a sorted list of all words in all documents together with pointers. This is an inverted index. And then the people from PostgreSQL said, let's use this for JSON documents as well, because a JSON document has fields. Name is Peter or something. City is London. And then in the next row there's another JSON document, and we simply indice the key value pairs. So here is age is 35, and it points to that document because in that document there is a field called age which is 35. And as this index is sorted, it is very efficient to search for all people older than 35, because we go to first of all age, and then within this age we search for the value. So it is sorted by the key. We create it like a normal index, but we say using GIN. I think there's now the approach of also a vodka index, because they said when there's a GIN index and there must also be a vodka index, but I don't know what this is about and if it's already implemented or if it's just a joke. So we index each key and value, at the top level of the JSON-B document. So if your JSON-B document has sub-elements, sub-documents, and then again sub-documents in that sub-document, these are not indiced. So only the very top level elements. So your fields that start after the first curly bracket. And here you see which operators are supported. This nice containment operator is supported. But also these predicates which check, so this one checks whether an element is in an array or a field is in an document, and so on. This checks whether one of many fields is in an array. This checks whether all elements are in an array, and so on. Okay, so it is now important to ask the right queries. So basically this query and that query, this query and that query is the same. Find all people that have the city Berlin in their profile. Here we make it with a containment operator. Profile has the following content. It contains city Berlin. And this one can now use the index. This cannot use the index because this does not check whether the city is Berlin directly. It extracts using this arrow operator what the city is, and then SQL checks whether it is Berlin. So this cannot use the index. So it is important to understand when index can be used and when not. If your application writes such a query to the database, you cannot accelerate this application by simply creating the index. You can accelerate this query as well, but then you have to create another index. We show an example later. But let's first of all try this out. I create a new schema, modern database concept on the 27th. Then I set schema path to MDC27. Search path it's called in PostgreSQL. Okay, now I create a table, create table people. People have a name, primary key, and the profile. Let's use JSON-B. And I insert some data, insert into people, values Peter, and lives in the city Berlin. And then the second row, Jane lives in London. Okay, when I now say search for all people who live in Berlin using this JSON operator here, we will see when we take a look at the execution plan. You can see the execution plan by writing explain before the select or by pressing this blue button here. You see the index is not used. A sequential scan always means O of n. So you have n rows and all rows are inspected. Is the city Berlin for the first row? Yes. For the second row? No. And this is done for all rows in the table. The reason why a sequential scan is used here, okay, first of all, we don't have an index. So the index is now there. I execute the query, the result is the same. And again, sequential scan is used. And the reason why a sequential scan is used, despite there is the index, is the data is much too small. So I have a trick on the last exercise sheet. I double the data in the table, insert into the table itself. Don't try this command for SQLite because this is an infinite loop. We insert the data that we get from the table itself. Some database management systems, like PostgreSQL, uses snapshot semantics. So they first evaluate this part, and then the result is a snapshot of the current table state, and then this is inserted again in the table. So basically, our table now looks like this. There are two people, Peter and Jane, and I double this. Oh, there's a primary key on that. Person ID int primary key, and then I don't drop it. I simply change the, let's say, name, and I concatenate select count star divided by 2 from people. So this gives me in the first iteration 2 because there are 2 rows, and then 1. So we have now Peter 1, Peter 2. I hope this works. Okay, we have Peter, Jane, Peter 1 and Jane 1. Then Peter 1, Peter 2, Peter 12. Looks good. Okay, now we have a collision here. This was not a good idea. Peter 128 already exists because it adds the 8 to a 12. I dropped the table and simply create it without a primary key. Without the primary key, we don't have problems. This got recommended to me and I have no idea what's going on. Recommended to you this insert. This is just for playing. You would never do this on a productive system. I just want more rows in my table, so I blow up the data. I have 1 Peter and 1 Jane, and I want 1 million Peters and 1 million Janes. That's why I use this statement here. So now I have 131 people, and now I search for all people. Let's use count star. Okay, 65,000 live in Berlin. How is this evaluated? Okay, on this bitmap heap scan, we see that the index is used. Here you also see the name of the index, people profile index we called it, and here we now see that it is used. If the index would not be there, it would be more costly to execute this query. Now the cost is 543 without the index. 533 is the cost. Without the index, the cost is 2,600. So before it was 500, now it is 2,500. So the cost is 5 times larger, 5 times slower than with the index. And this is just a cost, just a number. Higher number, more costly. It is not milliseconds or runtime, because the actual runtime depends on so many things, like how many other queries are currently running, what's how many RAM do you have, what's the CPU doing, and so on. So here we see that the index is now used. And for the other query here, the index is not used. Because the query evaluation looks a bit like, so I don't use count star now because I don't want to see the result. It is so big, I want just to count it. So this does not use the index because we don't have an index. Now I create the index again. And we see this index is not used because it executes this function, accessing the city value in the JSON field, and then after that it compares whether it is Berlin or not. So there the index cannot be used. So how does such an index look internally? Internally we index all field names of the top level document. So not field names within subdocuments. If here would be a subdocument job, curly brackets opens, and then company, job description, salary, and so on. If this would be a subdocument, then this salary and company would not be part of the index. So only the top level fields: born, city, country, hair color, job. If this would be an array, also no problem. Top level field name and each element of the array would be inserted here. Let's try this out. Let's insert another person. Let's call her Kathy, and she lives in multiple cities, in Regensburg and Stuttgart. Okay, here city is now an array. Let's now, there is now one more person, and then how many live in Berlin? So many. How many live in Regensburg? 0. Because we extract the city name. This does not make any sense for the array. I have to use the other function. Or I have to write it with a, so Berlin, Regensburg. Nobody has the city Regensburg, but one person has the city as an array which contains Regensburg. So now it is found. Now we find Kathy here. And now the interesting question is the index used or not? Yes, it is used. So this operator uses the index because in MongoDB we would call it a multi-key index, but here it is multi-key anyway because each document is inserted multiple times. So this Json documents appears 5 times within the index. So you see here 1, 2, 3, 4, 5 pointers do point to Susan. No, not this pointer, but here this pointer. So you see 5 pointers point to Susan because we insert a new document. Let's say the index already contains these 3 documents, and we insert a new document that has the following fields. Let's call her again Kathy, and then just 2 fields: born in 99 and X is 5, whatever this is. So then within the index 2 things are inserted. The born 99 will be inserted here, so it is already in the index. So another pointer will be placed here and shows to the new document, to the new row in our table. And this key is not yet there, so it inserts X5 and points it to that row. So After each insert, after each update, after each delete, the index has to be maintained. Yeah, and if X is not an array with 5, but with 1, 2, 3, then it now adds 4 items into this index. Born 1999, X1, X2, X3 to find it even if it is an array. That's how the Gin index works in PostgreSQL. So this is very PostgreSQL specific, and the idea is really nice in my opinion. So what's now with this query here? It does not use the index because we access the city value. This is a syntax that you would use for queries like give me the city of every person. Then you would use this arrow operator, give me the city, or group by the city. But for where predicates, where you are not really interested in the city, just accessing it for checking is it Berlin or is it not, this would be better. But let's say somebody implemented it already like this. There is an application which fires this query to the database and you cannot change it anymore. So this query here is sent to the database and you see, okay, I have my index, but this query cannot use the index. Yeah, it makes a sequential scan. Then the idea is I create a different index. Create index, people profile index, profile city index. I am only interested in this query. This index supports so many queries. Give me all people live in Berlin, give me all people that have the country UK, give me all people born after 1990, give me all people that have a job not equal to programmer or something. So this generalized inverted index helps you for all kind of queries that reference a top level attribute in your JSON data. So 2 questions are still open: how to support other operations like this here, and how to index fields that are not on the top level. So let's start with this query here. We want that this query is accelerated with an index, and for this you don't need a gin. For this you can just use a normal or did I now press Control Enter? For this index, a normal B+ tree index is sufficient, but not on the field profile, but on the result of the expression profile give me the city. This is a so-called expression index. Expression index also work like this. Create index blah blah blah, upper name index on the people table, on the upper of the name column. Select give me the people where name equals Kathy, finds this person. Of course, it does not use an index because we don't have an index on the name column. But we have now an index on the result of the expression upper name. And this now finds Kathy, and this now also uses the index. Expression indexes are not supported by all database management systems, but nowadays by many. So it works like this. We insert a new document, Kathy. What happens to this expression index, this B tree? We compute the expression upper of the name column. The result of that is capital A, capital C, capital A, capital T, capital H, capital Y. The result is inserted into the index, and this index can now be used when we use exactly this operation. So PostgreSQL is so smart that it sees, oh, here's upper name. I have an index which consists of upper name, and then it uses this index automatically. This is really nice magic going on here. And this can now be used to index the result of this expression here. This has nothing to do with GIN indexes or fancy extra data structures. We just extract the city name out of the JSON and insert it into the index. So now we execute our query. Look, is the index used? Yes, it uses this people profile city index. So that's the magic, creating a B+ tree index on a GIN. So, and when should you do this and not use a GIN? Two use cases. First of all, the application or the query is already given. You cannot change the query anymore. Then you need to create this index or create two indexes, one GIN and this one. Double cost of insert, update, delete, but okay. Therefore, you increase both kinds of queries. And the second use case is if you never access country, hair color, if you never make selections on all these other fields in the JSON, then it would be a waste of research, a waste of resources to create a generic index. If you know I will only search city equals Berlin, city starts with a K, city is Regensburg, city is not Regensburg. So if you only are interested in one field, the very best idea would be making a column in which you write city and not the JSON field, but that's not an option for now. Then you simply create an expression index. Now this query can be used. And now only this query can be used, because this query must contain the operator in exactly the same way as the index was created. Now the query from the two slides before, this here, is not supported anymore. If we execute this query, give me the people who live in Berlin, you see it uses an index, but it uses the old GIN index. And if this index would not be there anymore, then it has to again make a sequential scan. And only if you write people have the city equal to Berlin, then our index can be used, because this expression is exactly the expression how our expression index is defined. So this is now important. You have to match your queries that you write to the indexes that you have, and vice versa. And these expression indexes can now also be used to create a GIN on a sub document within the JSON. So here, okay, this is not, I don't have an example here, but let's create an example. Let's create a new person, insert into people. Let's call him Dave, and Dave has the city Regensburg, and Dave has a field called job, and this is a JSON document again, company SAP let's call it SAQ for not using a real company name here, and again salary, something like this. Okay, no index that we created so far could use queries like find all people that work at the company SAQ, because only the top level fields are indexed. So only city Regensburg is in the index, and job, the whole document, is in the index. But we don't make a selection on the whole document, including the salary and all other fields. So yeah, so we have to create a separate index now. Let's first take a look of how our query is. We want to find Dave. Select star. There are so many questions now in the chat. I will come to all these questions when I go to the next slide. So simply write your questions there. So give me the people where the profile I go into the field job has the company SAQ. Okay, it finds Dave, because when I go into profile company, this is not a double arrow, so it does give me a JSON, and in this JSON I search if the company field is there and has the value SAQ. Of course, it does not use an index. This is not possible. So I create now, create index, let's call it people profile job index on people. We're using a gin. And the expression now is, yeah, like here, we go into the job. So the result of this expression is not a varchar like we had in our profile double arrow city. Now it is a JSON, so we create a gin index. So if you ask yourself, when do I write gin, when do I not write gin? When your column or your expression is returning or holding a JSON or JSONB value, then you create a gin. When your expression or your column is a scalar value, integer, varchar, date, and so on, then you use a B tree. So the index is there, and we check. Yes, our people profile job index is used here. So the last question in the chat is my favorite one. It is just answered it. I'm always interested in what questions you had. So my JSON looks like this. You have a document that has an address field, which is again a subdocument, city Fuba. Would that index be able to give me all people living in Fuba? No, you need to create an expression index on, am I mirrored, verkehrt, mirror. Here's my left, and this is, don't know. Let's, no, it's not mirror. So you need to create, because I looked to this arrow from my side here. You have to write this arrow operator and go into address. And then the top level elements in that address object are now indiced. And the top level of the address subdocument is zip and city. What's the benefit of using expression indexes? So in general, an expression index is the solution to index expressions. So to allow queries where you use expressions to use an index. You sometimes have queries that use not directly a column where city equals Berlin, but sometimes you have queries that make an expression on that column where the fifth letter of the city is a B. An index cannot support this operator. The fifth letter of the city is a B. This is only possible with expression index. So expression indexes are the solution to support fast index supported search on expression queries. And for JSON data, we often have expressions with all these operators and so on. And for non-JSON data, yeah, the expressions are like uppercase, lowercase, and so on. So when you implement a search, give me all people with the first name Peter, you want a case insensitive search. Then you don't make an index on the first name column, you make an index on the lowercase first name column. And then when you query it, you search for the lowercase, so that you simply throw away the case, so that your index works for a case insensitive search. A more complex scenario are so-called expression joins. This is ugly. This is so extremely dangerous. When you don't know what you do, don't do it. So you have a query, and then a typical join looks like this. A join B on A.x equals B.x. This is a very nice join query. But this is not a nice join query. So you look in the X column of your table, convert this into uppercase format, and search for join partners in the other table, and again convert it into uppercase. So this is a very ugly join, and this will not use an index. So this is a nested loop join. So when your table A has n rows and your table B has m rows, then the cost of this is O of n times n. And this is very costly. And to accelerate even those expression joins, then you need to create an expression index. So an expression index is again something where you need to know, how does my query look like? My query looks like this, and then you must be so smart to create the index on the right expression so that your index is used for this query that you want to accelerate. Okay, do you have more questions about indexes? Expression indexes are good to know. You learn the fundamentals of indexes in the basic lecture for database fundamentals, but there is so much about indexes that you only learn when you go deeper into that topic or you look into documentations. For example, did you know that you can write in an index, this is my screen, create index, people name index on the people name. This is an index that you know. It supports for select star from people where name equals Dave here the index is used, you know, but did you know that you can say where name like d%? This is called a partial index. I only put those documents in the index that fulfill this where predicate. Or if you have a different column here, like where, yeah, let's use our Json, where profile city equals Berlin. So the in profile where like I drop this. So this is now a query, and all documents that fulfill this predicate are now in the index. So this index is never used, even if a person lives in Berlin. So here Peter lives in Berlin, but the database system does not know that. So the index is not used. But if I say and then this expression here, then the index is used, because it sees, oh, here's an and predicate, the city is in Berlin, city is Berlin, and all the people who have city Berlin are part of the index, and I'm searching for people whose name is Peter, so I can use the index on the name. So this is also extremely nice to only index a part of the element, not a part of the rows, and not all rows. Because you all know indexes are not for free. Indexes accelerate your queries, but they slow down DML queries, insert, update, delete. And when you say, I only put those in my index where a specific column is null or is not null, then some documents don't affect the index when you insert, update, or delete them. Those where this column is null or not null. And for the index on a subfield of a JSON, I said, okay, it is a waste of resources to index the whole JSON document if you are only interested in queries where city equals something like that. First of all, you save space, but the more important, when the job of a person changes, this does not have an impact to the index when you only index the subfield city. So that expression join would need two indexes? No, just one. One for table A.x, yes, and one for table B.x, no. And internally the DB does this via join? No. It's much easier. So do I have my my join query here? No, my join query is gone. It looked like that. Select something from A join B on A.x, on upper A.x is upper B.x. You only need an expression index on A.x or on B.x. Both are not required. One is sufficient. So if you have an index here, your database system scans all the rows in the table B. Here is Peter in that X column. It converts it into uppercase. The result is Peter in uppercase. And then it uses the index on the table A, on the column X, to find the join partners. So the cost is not O times n, O of n times n anymore, but it's just O of n, if these are the rows in the in this table times and then the cost of the index. If it is a tree, then O of log of m. If it is a hash index, then yeah, then just that one. So if you have the choice, create the index on the bigger table, because then this is the smaller one. But it is still possible to use a gin for nested fields by simply writing the query accordingly. Select count star from product where data address did you try this out? I would say this does not work. Let's drop all our indexes. So where do I have my job index? I think here. I drop it. And you say, when I create the normal gin index and you write, give me the people from people where profile contains the job field and it has the company as a queue. It finds Dave and it uses the index. Okay. Yeah, maybe I was wrong. Maybe it is because we introduced this top level field here. Okay, this is a good point that I did not know. So the index is even used for this query where we make a search on a sub column, but maybe because of this full path here. If we would make a query where we don't know in which field, this could not be expressed with this operator here, but within some nestings, maybe with a path query or so, where, so in XPath we would write this, or in JSON path we would write this. So when we don't know exactly where the field is where we want to search in, maybe that's the point. But then even an expression index cannot help. Okay, good point. So it shows us that this gin index is even more powerful than I know, than I thought. Thank you for that hint. So our gin index would even be used for this search on a sub document, on a subfield. I said PostgreSQL supports gin, and I like the gin, and I don't like gin, but I like the generic inverted index, and other database systems don't have this nice index structure. So I show you some tricks how you can index your JSON data in other database management systems. One trick you already know, using expression indexes. So Oracle supports expression indexes. You have a JSON column called profile again, and you want to accelerate queries that go into the JSON field city. You create this expression index on the result of this expression here, and so every city goes into that index and points to the rows that have this city value. I want to open this here. So my people table in Oracle now uses here the character large object types, and it checks whether it is really a JSON. We insert people who have a city, then we create a city index, and then we make a query and use this expression JSON value profile $.city, this JSON path expression here, like we defined our expression index, and then you see in the explain plan that the index is used. And in Oracle it's even used if there's only one row in that table, so we see that it is used. In MariaDB there's a nice approach called virtual columns. You can add a column to a table. That's something you already know. So we can add a column to a table, and then we can store data in it. But in MariaDB you can say as. So you don't store data in that new column, but Oracle will automatically store in that new column the result of this expression. And within that expression we can use functions, access other columns of the same row. I don't know if it supports subqueries, but here in this case we add a column called profile city. Let's take a look into MariaDB. We will see that now our table has a new column, and it stores always the result here of this expression. So our person has city Berlin, and here profile city is Berlin. And when we make an update in between, update people set profile equals to something where name is Peter. So we want, I don't know the MySQL syntax to change a single field. Let's say London. Then it shows London, so it is lively executed. This is why it's called virtual columns. There are two possibilities: persisted columns and persisted virtual columns and virtual columns. So it depends on is it really stored somewhere, this London value in a column value, and it's just for convenience that we don't need to put it there, or is it like a view? Is it computed when we query the table? And the default is it is virtual, so it does not store it really there. When we say give me the profile city of a person, then at this point in time it computes the expression behind that column definition. This is an expression like an expression that we use in a view, and when we query the table, it sees, oh, I need to compute what's the value here. So it computes the expression behind that column at runtime. And even if this is virtual, MariaDB supports indexes on these virtual columns. So create index on people profile city. So this is not a normal column, this is a virtual column, but MariaDB implemented it in a quite new version that indexes are supported there. But then you need to write your query, not like here in Oracle where we said, oh, give me here the JSON value, blah, blah, blah. Then you need to write the query on that virtual column, because this virtual column is now indiced. The index does not know that the value in that column has its origin from a JSON document. So again, the user that queries your data has to write a query so that it matches the index. So I need to write it like this. It is not supported to say JSON value profile city equals Berlin. So you again see even before it did not use the index. Why Berlin? He lives in London now. Yeah, it does not use the index because the table is again too small. Oh no, it uses it here. Simple. And here we see it uses it, but now I use the expression behind that. Yeah, using where. So this is a full table scan now. Type all. And profile city. Type ref. Okay, so it uses the index only if you access it via a where predicate on that virtual column. So these are some tricks how to index data in a JSON field. But to conclude, JSON is very nice to have semi-structured data, flexible data, arrays, subdocuments, arrays of subdocuments, complex arbitrary data. Therefore, JSON is nice. If you often query the same things again and again, like we did here, give me the people who live in Berlin. If you do this very often, think of not storing the city in JSON. Extract it to a real column. The things that you need very often, put these into real native SQL columns. Then the relational database system can make use of all optimization techniques, histograms, statistics, indexes, and so on. So think of mixing it right. So, a conclusion. Write your questions into the chat while I read out the conclusion, what we did in this chapter 3 about composite types. We started 2 weeks ago with a lecture on user-defined data types. Create type address, and then this column is of type address. And we had composite types. The SQL standard has types for arrays, for multisets, for row, and we saw how different relational database systems implemented them. SQL XML is the standard to support the XML data type. This column is of type XML, so we store XML data in it, and then we saw how to write XPath queries on that data, how to make predicates, whether an XPath query produces a result or not. And we took a look on SQL JSON. JSON data type, JSON B in Postgres, or other JSON data types in the SQL standard. So we took a look at the difference between native JSON storage or storing JSON as a string. In PostgreSQL, we had many examples. We took a look at the two data types, how to build JSON with build object, builds an object, and we have an aggregation function that collects everything in a new JSON array. This was here this JSON B aggregate. we had different operators for accessing a field and then again having a JSON, or accessing the value within a field as a varchar, as a text. A function that checks whether an element is in an array or whether a key is present. This nice operator which checks if a JSON document contains another one, and how to do path expressions for this JSON path with a $dot something within the database directly to support even more complex operations with an or so. And today we took a look on indexes on JSON data, the generic inverted index for generalized inverted index for indexing a whole JSON document, all its keys and all its values for quickly searching something within a document, and some tricks how to use expression indexes to evaluate an expression on the JSON and index the result of that expression to avoid that the whole document is indexed when we don't need it, and to support indexes even there where we do not support it natively, for example because of Oracle or another database system does not support a GIN. Virtual columns is the other workaround for MySQL in that case. No, not MySQL, MariaDB, where we add an index on a column that's not natively there, but it's computed. So basically a derived column, derived by other attributes. Okay, the next chapter is already online, but I think it makes more sense to have to change the title of this video. No problem, we are good in time. We start with the next chapter about NoSQL databases next week. So this week was on indexes on JSON data and concluding the SQL JSON. I hope you learned something new about indexes, even if this has nothing to do with JSON. And so it is always good to be an expert on indexes because performance matters so much, and everybody should know what indexes are and how to use them in the right way. Okay, are there questions about this chapter here? The videos are lively streamed on YouTube and publicly available. So if somebody saw this video on YouTube, oh, we'll talk about NoSQL, and I didn't talk about NoSQL, see you next week, then it's actually about NoSQL. But I will rename this video now, give it another title. No new exercise. Yes, it's a good idea. We have 12 exercise sheets and less than 12 weeks, so we do not need to make an exercise sheet every week. Yeah, no exercise sheet this week and no sessions this week, no slots on Friday. So see you next week on Tuesday to the next lecture, and then we introduce NoSQL databases, what they are. It is a very compact introduction to NoSQL. Is here somebody, please write in the chat, who already participated in a NoSQL lecture? I think there were some people. Because this is a lecture on modern database concept. NoSQL is a modern database concept, but we don't go so deep. yeah, there are some people writing yes. MongoDB, yeah. I will give an introduction to NoSQL so that everybody knows what NoSQL is, what typical systems are, how they work, and then the rest is not part of this lecture anymore. So we will do Redis and HBase next week and take a look at MongoDB and Neo4j in the upper next week. And Neo4j is a graph database. And we will focus after that more on graphs, because graphs are a very nice advanced data structure. We will take a look at how to work on graphs without a NoSQL database, how to work with graph data in SQL, make recursive queries using connect by operators, using with recursive, looking at a language RDF. So after that we will focus on graphs, and then yeah, that's the outlook for the next weeks. Yeah, so you will learn a lot about NoSQL even if you don't know anything about it. And the ones who already participated in the NoSQL lecture, I think you will also learn something new, because we have a different focus here. Okay, then see you next week. Have a nice week and a nice weekend, and tell your friends that there is no exercise on Friday. Okay, see you then. Goodbye.